Just wanted to begin again with a few comments about the test that's coming up. So I placed in the assignments subdirectory a Canvas practice test that will have the same format as next week's test 1. So it has 5 multiple choice questions on it. They're each worth 4 points. It has 6 numerical answer questions where you submit one numerical answer. They're each worth 10 points. And then there's one fully worked out problem where you'll write out the solution and you'll submit as a PDF or a JPEG that fully worked out solution. And that's worth 20 points. So you'll want to try that out. That'll give you an idea, as I say, about the formatting, the style, etc. of the Canvas test. Just as a reminder, the content is all the content since we began our class. So it's chapters 1 through chapter 4. It's the work we did on dimensions and units in lecture 1, but then it's mostly work on kinematics, describing motion, and the most famous examples are falling bodies and projectiles. And then it's more recent work on the laws of motion, how forces influence motion, and Newton's laws of motion, and what we've been talking about in the last class, equilibrium and non-equilibrium. Anyway, we're going to continue that story today. Any questions from about the test, or any questions before I get started? I'm trying to look at the chat here. Oh, question, when is the practice test due? The practice test is just going to be open. It's just for you to try out. So if for some reason it goes away, I don't want it to go away. You should be able to just try it out. Is the test open note or just the formula sheet? It's open note, open book. So you can use your notes, you can use the formula sheet. You can use the book or the ebook. Any other questions on the test? Okay, well, if you have any questions, you could put them in the chat and I can answer them at the end, obviously, or if I see them during the lecture, or you can send me emails or whatever if you have questions about the test. Let's then get on with today's content. So last class, we talked about 3 forces. We talked about gravity, normal force, tension force. And we looked at examples of gravity, normal, tension forces in situations where there was what we call equilibrium, and situations where there was what we call non-equilibrium. So in equilibrium, although there were individual forces acting, the individual forces add up to make no net force. And so there's no acceleration. So an object at rest stays at rest, for example. In the case of non-equilibrium, then the individual forces that are acting add up to make a non-zero net force. In that case, there is acceleration, and the acceleration is described by the second law of motion, Newton's second law. So in today's class, we're going to really continue exploring, working with, illustrating Newton's laws of motion, but to gravity, normal force, and tension force, we're going to add frictional force. And so those are going to be our cast of characters. We're now going to have 4 characters: gravity, normal, tension, friction. And as we work through gravity, normal, tension, friction examples, illustrations, we'll also look at both cases of equilibrium and non-equilibrium. Okay, the first thing I want to do though is an example I was hoping to do at the end of last class, but I didn't do it at the end of last class. So I'm going to do it at the beginning of this class. It's an example on pulleys, and there's pulleys on the homework. So that's why, thank you whoever pointed that out, that I've delayed the homework collection to tonight. So let me introduce the problem on pulleys by first reminding you of a problem of a block on an incline. This is a very famous problem in physics. You always do blocks on incline in physics. You can't get away with not doing blocks on incline in physics. And what we learned in last class, and the important thing about the incline in last class, is that on a frictionless incline, the acceleration of gravity, that 9.8 meters per second squared, it gets diluted on the incline. And on the incline, you just see a fraction of that acceleration of gravity. And that fraction is determined by the sine of the angle of the incline. So that's kind of the dilution. The dilution is sine theta. And that allows you to slow down gravity's pull and better explore gravity's pull. And so that was a big breakthrough in the last class to sort of so clearly understand how the incline impacts the acceleration of gravity. Well, when we look at pulleys today, we're going to see a similar thing, that actually pulleys, so in this sketch here, there's a pulley in the center. It will rotate about its center. There's a string or a cable or a wire that's slung over the pulley. And then over here on the left is a mass attached to the left-hand end of the wire, and over here on the right, mass attached to the right-hand end of the wire. And if you were to release this arrangement of the masses, you set it up, you hook on the masses, you let it go, then you would discover that, well, the heavy one accelerates downwards, the lighter one accelerates upwards. That acceleration is not the acceleration of gravity. Again, it's a diluted version of the acceleration of gravity. And we're going to discover how much it dilutes gravity. It dilutes it by this factor here, which if you look at it, is the difference in the masses divided by the sum of their masses. So a very simple result. And we're going to figure out how that comes about. How does that dilution of the pull of gravity come about? So that's really our plan. Let me go on to work out this problem of the pulley and the two masses. I just noticed if you've got questions about the test, I'll answer them at the end of the lecture class rather than try and throw it in the middle of solving a problem. I'd never be able to do that. So I'll answer any test questions at the end of lecture class. So to be a little bit more concrete, I'm going to think of this situation here. We got the pulley, we got a mass on the left, mass on the right. The one on the left is 520 grams. The one on the right is 500 grams. So this one in green is slightly heavier. This one in blue is slightly lighter. And so you probably intuitively know that this one on the left will fall because it's heavier. This one on the right will rise because it's lighter. Let me just show you a demonstration of this, if I can. I'm just sharing another screen here. And you're going to see exactly that arrangement of the 520 and the 500 gram masses. And the way I'm doing it is actually I had two 500 gram masses and then I added a 20. And now the left-hand side has got the extra 20. And you see the one on the left falling, the one on the right rising, and that's under the pull of gravity. Let me just stop it for a second and I'll slow it down so you can see it even more clearly. This time I'm going to reverse the two masses. So now I'm putting that little extra 20 grams on the right rather than the left. So the right is now going to be heavier. The left is going to be lighter. And let's see what happens. And when I release it, the one on the right now heavier falls down. The one on the left now lighter climbs up. And they're falling or rising under gravity, under a diluted, like a diluted pull of gravity. Okay, so let me go back to the lecture slides, if I can here. I don't know if you can hear the drilling and the hammering and all these things that are going on around me. I'm basically giving the lecture from a demolition site, it feels like right now. Anyway, so here's a picture again of a pulley in the middle in gray, mass on the left and mass on the right. But this time I've added to this picture all the forces that are acting on the two masses. And this is the crucial step in figuring out the acceleration. So let's start on this mass on the left-hand side, the heavy one. There's two forces acting on it. There's the weight, its weight, due to its mass, and that's a downwards force in red here, and it's just mass times the acceleration of gravity. And then, because it's connected to the string, like an apple connected to a stem in a tree, this mass connected to a string over a pulley, there's tension in the string. And so I've denoted the tension force here in blue. And because this is mass number one, I called the weight W1, I called the tension T1. And those are the two forces that act on the left-hand mass. I did the same thing for the right-hand mass over here. You know, it's pulled down by the force of gravity, pictured here in red. That's its weight. And its weight is its mass times acceleration of gravity. And then also it's connected to a string, and that string is wrapped over the pulley. It's pulling upwards as a tension force acting on the block. And I called that tension force T2. I called that weight W2. So those are the pair of forces that are acting on the pair of blocks, tension and weight on both the left-hand and right-hand blocks. Let me make a few important comments. So the tension on the tension force on the left-hand block and the tension force on the right-hand block are actually the same. So it's a single string that's wrapped around the pulley and connecting the two blocks. So the blocks are sort of pulling on each other by this single string, and those tension forces that they experience are like sort of equal and opposite forces. There's two tension forces, and so they experience the same size tensions. And so I've denoted that fact by just writing T1 and T2 as just T. They're the same tensions. There's something else that's the same that's interesting. So these two forces on the left-hand block add up to make a net force that creates acceleration. These two forces on the right-hand block add up to make a net force that creates its acceleration. The accelerations for the two blocks on the left and right, whilst one is up and one is down, those accelerations have the same size. If they didn't, think about it. Those blocks are connected by a string. If they didn't have the same size, then either the string would go limp or the string would break. So because they're connected by the string, those two accelerations are also the same. So I don't need to call them A1, the acceleration in the block on the left, A2, the acceleration of the block on the right. I just need to call them the acceleration. One final comment. When I turn this picture into equations for these forces, I need to pick a direction as the positive direction. And this is how we do it on a pulley. So look, the mass on the right is going to climb up towards the pulley. The one on the left is going to fall down away from the pulley. We denote that sort of counterclockwise rotation around the pulley as the positive direction. So for example, the weight on the left-hand block, that's in that positive direction. The tension on the right-hand block, that's in that positive direction. The tension on the left-hand block is in the negative direction, opposite my arrow. The weight on the right-hand block is opposite my arrow in the negative direction. So that's our convention about directions on a pulley. It's a little bit more complicated than, you know, if you just have motion in a straight line. Okay, so now I'm going to make that diagram into two equations, and I've written these two equations downstairs here. Let me get my annotation going. It'll only take me half an hour to do that. I'm going to think about this mass here, m1 on the left, and I'm going to write down Newton's second law for it. Force equals mass times acceleration. And I'm going to think about this mass on the right, and I'm going to write down Newton's second law for it. F equals ma. And that's what I've done here. This is the one on the left. And here, this is the one on the right. So the sum of the forces on the block on the left, I should have put a 1 here, actually. There should be a 1 here and a 2 here. The sum of the forces determines the acceleration of on the block on the left. And likewise, the sum of the forces on the block on the right determines the acceleration of the block on the right. And so I then just filled in my particular forces for this arrangement of two blocks in a pulley. So for the one on the left-hand side, here are the two forces. There's the weight downwards, that's in the positive direction. And then there's the tension upwards, that's in the negative direction. And so here's the weight of the block with a plus sign indicating it's in the positive direction. Here's the tension with the minus sign indicating it's in the negative direction. And those two guys add up to determine mass times acceleration for the block number 1. And then here's exactly the same thing downstairs here for the second, the right-hand block. So there's weight, that's a force acting on the right-hand block. It's opposite the direction of motion of the blocks. So it's the negative sign here. Then there's tension is acting in the direction of motion. And so that's the positive sign here. And those two forces add up to make the net force, which again determines the acceleration, this time of mass 2 rather than mass 1. And so that's what we see there. So that's the math. Yes, the sort of quantifying the picture, writing down the equations that go with the picture, writing down second law that accompanies the picture. So now let's go on to actually calculate the acceleration. And that's what I'm going to do here. So if you look upstairs here, I've reproduced those two equations from the last slide. The only thing I did slightly differently when I wrote them down was, look, I've written the weight of the two objects as in terms of the masses and the accelerations of gravity, but that's the only difference. And then what I'm going to do is, if you look at these equations, right, they're two equations, 1 and 2 I labeled them, and they got two unknowns. The acceleration is unknown, and the tension is unknown. And so I'm back to this old problem from, you know, high school math or whatever it is, or elementary school math, I can't remember, of solving two equations for two unknowns. And so now I've got a math problem. I've no longer got a physics problem. This is just a math problem. So how would I do that? Well, in this case, it's actually, there's a really simple trick to do it. The trick is to add together equation 1 and equation 2 to make the sum of the two equations. And that's what I'm doing in this line here. I should erase all this junk, shouldn't I, that's appeared in the last slide. I'm going to add together these two equations. Now, what I mean by adding them together is that I'm going to add the left-hand sides together and add the right-hand sides together. And if you've got two equations where the left hands equal the right hands, and then you add them together, well, the summed left hands and the summed right hands must still equal each other. And so that's what I'm going to do. And the interesting thing is when I add together the two left-hand sides, the negative tension in equation number one, the positive tension in equation number two, they cancel out. And so there's no tension. It goes away, vanishes. When I add together the right-hand sides, then I get mass times acceleration for the first mass plus mass times acceleration for the second mass. The other thing I did when I added the equations together was on the left there's a common factor of g, on the right there's a common factor of a, so I pulled out those common factors. Now you can immediately see how I can solve for the acceleration. I just divide through by the sum of the masses, m1 plus m2, and I get this little magic equation here that says the acceleration of the masses, one of them's down, one of them's up, depending on whether they're the heavier or the lighter one, is equal to the acceleration of gravity times a factor that involves the masses. And that factor is simply the difference in the masses divided by the sum of the masses. And so for my particular example of a mass of 0.52 kilograms and a mass of 0.50 kilograms, I filled in the mass difference is the 20 grams or the 0.02 kilograms. The mass sum is 1.02 kilograms multiplied by the acceleration of gravity. Here's my diluted acceleration. And so that's the answer to the problem. And it's an explanation of where this dilution of the acceleration of gravity comes from. So the closer and closer that you make the masses to the same value, the smaller and smaller the acceleration becomes. And if you make them the same, they just hang there because one's not heavier than the other. So no one of them can choose to fall and the other to rise. It's a stable situation. Once you've got the acceleration, it's then easy to figure out the tension. Because you could go back to equation number one and say, well, look, I know what the acceleration is now, so I can just rearrange it for the tension. I did that here. Or you could equally as well use equation number two, right? And go back and say, well, now I know the acceleration. I can rearrange it for the tension. And so you could use either of these two equations, and you find that in our particular case, the tension in the string is 5 newtons. And so that's how we solve that problem. It's a problem that to me that looks kind of intimidating to begin with. You know, I kind of want to run away from it. But then once you set up the picture and once you set up those pair of expressions of Newton's second law for the two masses, you start to see the route to the answer and the acceleration and the tension. It comes out quite neatly and nicely, I think. So it's a very nice example in physics. And just like the incline, you're not going to get through a physics class without looking at a pulley. It's unavoidable. It's unpreventable. Okay. Let me clear this junk. And let's go to the next slide. Okay, next slide is a quiz. So on the pulley problem. So let me publish that, and then I'll give you just 2 or 3 minutes to do the quiz, and then we'll move on. The force on the heavier mass is larger. The force on the lighter mass is smaller. They both accelerate with the same acceleration, which means that to both accelerate with the same acceleration, the heavier one must experience a larger net force, the lighter one a smaller net force. It's like to accelerate an elephant and a mouse, right? With the same acceleration, you're going to have to exert much more force on the heavy elephant than much less force on the light mouse. So it's an example of that. Anyway, I think you all knew it. And now I'm out of control with the slides here. Okay, now I want to bring in friction. So this slide introduces friction. It introduces it in a way where we compare it to those two other contact forces that we met, which were the normal force and the tension force. So friction is also a contact force. All three of them involve the contact between materials. In fact, all three of them are due to the molecules of the materials in contact. So over here on the left-hand side, right, this guy here, oh, here was the normal force. Here was the tension force. And here's friction force. So the normal force, if you remember, arises when we place the apple on the table. The atoms of the apple and the atoms of the table are squeezed together and they push back. And that's the origin of the normal force. If you remember the apple on the stem of the tree, right? The tension force, the origin of the tension force from the stem on the apple is that the atoms of the apple and the atoms of the stem, not the table here, they are pulled apart and the atoms and molecules pull back. The origin of the friction force is shown in this picture. So I'm depicting friction in this picture. So the friction I'm thinking about is, here's a crate, and the crate is being pulled. It's being pulled to the right by a person's force, an external force, but the crate to slide along the floor would experience an oppositely directed, a sort of resistance, a frictional force. And that frictional force here that I've labeled F subscript F for friction is, it's not due so much to the atoms of the crate and the floor being pushed together or pulled apart. It's just to do to their stickiness. The atoms and molecules like to stick together, and you've got to sort of break them apart, pull them apart to slide the crate towards the right across the floor. And that's the origins of friction. If you want to think about normal and friction forces, the normal force is sort of a parallel, the perpendicular component of a contact force, and the frictional force is like the parallel component of that contact force that you get when two surfaces are in contact. So the normal force and the friction force are kind of closely related components of an overall contact force. Okay. Let's go on to the next slide. And we're going to, in this slide and the next slide, we're going to make a distinction between two different types of frictions. And we're also going to write down some equations describing these frictional forces. This one's static friction. So this is, imagine this is me and I'm pulling on this crate. If I'm not moving the crate, if I'm unable to move the crate, although the crate isn't moving, because I'm pulling towards the right, there must be a balancing frictional force towards the left. Otherwise, the crate would move. And that frictional force, there's an equation that we use for that frictional force. This little bit shouldn't be here. That the maximum static frictional force is equal to the normal force, which is depicted here, which is balancing gravity in this situation. So here's the normal force, times a number. It's just a pure number. Doesn't have dimensions, doesn't have units. It's called the coefficient of static friction. And that product of the normal force and the static friction coefficient sets an upper limit, an upper bound on the maximum size of the static frictional force. And that's what's labeled here. So for example, if I wasn't pulling at all towards the right, there would be no frictional force, static frictional force towards the left. There'd be no need to balance my pull because there was no pull. And that obeys this limit, right? Zero static frictional force obeys that limit. If I start to pull towards the right, then I start to get a frictional force that's balancing my pull towards the right with a friction force towards the left. And the harder I pull towards the right, the harder the frictional force resists towards the left until you reach this maximum value. Once you reach that maximum value or exceed that maximum value, the crate would start to move or slide. So that's a limit on the static frictional force. It can be anywhere between 0 and this maximum value of the coefficient of static friction times the normal force. Let me do the next slide. Next slide is going to be kinetic friction. Here we are. So this is the other category of friction. Static friction applies when something is stationary. Kinetic friction applies when something is moving. So we could have called them stationary friction and moving friction. That would have been perfectly fine too, instead of static and kinetic. So now, this is me again, and I'm pulling on the crate, but this time I'm pulling hard enough that I got it moving. So I'm pulling towards the right, and the crate is actually now sliding across the floor. Well, static friction no longer applies because it's moving. What we've now got is what we call kinetic friction. And this is the formula for the kinetic friction. And again, it's in proportion to the normal force. So here's the normal force N that's balancing the gravitational pull W. But now it's multiplied by a new number. It's also dimensionless. It's also unitless. It's the coefficient of kinetic friction, and that's this mu here. So the product of mu k and the normal force determines the kinetic frictional force. Now, this is a little bit different equation. And for the static frictional force, it just said that the static frictional force can be as large as mu s times the normal force. For the kinetic frictional force, the kinetic frictional force actually is mu k times the normal force. So that's a difference too. Okay, here's just to stress these two types of friction, right? Here's a picture showing basically a graph. It's a graph of, this could be the crate and me pulling the crate, or for some reason in this figure, right, it's a garbage bin and me pulling the garbage bin. So here I am pulling towards the right and taking out the garbage, basically, in this picture. That's what it must be. Obviously, the author didn't take out the garbage and was getting told off for not taking out the garbage, put in this figure. Anyway, I'm taking out the garbage by pulling the garbage bin towards the right. And as a result, there's a frictional force to oppose that motion towards the left. And this graph downstairs here, so that the horizontal axis, a nice straight line, that's the force I'm applying towards the right. And this vertical axis, that's the frictional force that's being opposed towards the left. Now, down here in this corner is where I'm applying no force. I'm not taking out the garbage. And so there's no frictional force. And then I, say, oh, maybe I'll take out the garbage. So I start to pull it a little bit. And as I pull the garbage bin a little bit, a frictional force grows. And that's what we see keep happening along here. Along this straight line here, there's no motion of the garbage bin. I'm not yet actually taking out the garbage. I'm just pulling on the garbage bin. And as I pull harder and harder and harder and harder, the static frictional force pulls harder and harder the opposite direction. Nothing's happening. And then suddenly, this moment, this instant, this is when I pulled hard enough that I actually get the crate moving, or get the garbage bin moving. And then after that point, well, the harder I apply my force, the kinetic frictional force is now always constant. It just takes this value here. And so this graph here is really a picture of the fact that this would have been better to put this is less than or equal to that. It's really a picture of how friction works, how these domains or phases of static friction and kinetic friction work, and how over here on the left, static friction has varying sizes from nothing to a maximum. Kinetic friction, on the other hand, has a constant size over here on the right-hand side, no matter what force I apply. Okay, let's get rid of all the junk and let's go on to the next slide. Just a couple of quick, I'm going to be really quick on this slide. So there's some sort of rules about how kinetic friction, static friction works, some sort of properties that static friction, kinetic friction appear to obey. One is that the static frictional force and the kinetic frictional force, they don't depend on the area of contact between the two surfaces. So what have I got here? I got Kroger's peanut butter. I always have some by my side. And if I place that on my hand, there's the same static frictional force if I place it this way or this way, or same kinetic frictional force, whether I place it this way or this way. So it doesn't matter whether I pull a table across the floor on its legs, I experience a frictional force, or if I turn it upside down, I think, well, I'll turn it upside down, I get less friction maybe. Pull it on the face of the table, there's going to be the same frictional force. It doesn't matter whether the area is big or small. That's what I tried to show you in this little cartoon here. This is a block with a small area in contact with the table, same block with a large area in contact with the table. Friction is the same in both cases. The other thing that friction doesn't depend on, and you probably could have seen it in the last graph, is that whether I slide something fast, slide something slow, there's the same kinetic frictional force. So that's the lower cartoon here. I got the same block again. Here I'm sliding it slowly across the floor. I'm slowly taking out the garbage, complaining all the way. And then here, I'm quickly taking out the garbage at high speed because I just want to get it done. And the frictional forces are the same in both cases. Now, one remark about these, I call them rules. They're not fundamental laws. F equals ma, second law, is fundamental law. These are just rules of thumb, really, and they're probably not exactly right. Probably at some level, the frictional force does depend on the area in contact, does depend on the speed in contact, but really not very much. And we treat friction as if it doesn't depend on the area and it doesn't depend on the speed. So they're not F equals MAs. They are rules of thumb. They are guides to friction. Okay, show demonstration of coefficients of friction. Yeah, let me show you a little movie here at this point. And that means I've got to share a different screen, if I can. And so here we go. I'm in the chemistry physics lecture room, and I'm going to show you about frictional forces depending on the surfaces that are in contact. So this is a block. It's a nice block. It has these 4 surfaces that each have different materials on them. This one is rubber. There was a shiny aluminium surface. And then there was a wood and plastic surface. Now I'm just showing you, I'm hanging the block from this device that measures the tension in the string. You didn't see it. I'm going to slow it down at this point. I'm going to slow it down because what I'm going to do is pull the block on the 4 different surfaces across the tabletop. And what you're going to watch, one thing you want to watch is the little meter that I have attached to the block on the string. It measures the tension in the string. It measures the force that I need to pull the block. And so if there's different frictional forces acting on the block, I'll have to pull different amounts to move the block. And you'll see the different frictional forces because the meter will read different forces. And you'll be seeing essentially different coefficients of kinetic friction. And so this is a way you could measure kinetic friction. And this is a way we can see the different kinetic frictions of these different surfaces. Now you might guess that, one of the surfaces was rubber. Now rubber are used for car tires, and they're used for car tires because there's lots of friction and you want that. You don't want them to slip or slide. Then another surface, right, that polished aluminum and that plastic, that's not so much friction. That's kind of slippery if you were to walk on that or run on that. And so you'll see less frictional force there. Let's watch the movie. So now I've got it on the rubber, I think, and I need 4 newtons. You see the arrow at 4? I can just about see it. It's getting, camera lighting wasn't, I didn't have a great lighting crew on this one. It's a great sound crew, but not a great lighting crew. So that was 4 newtons with the rubber surface. Now I'm going to put this polished aluminium surface, very expensive, in contact with the table, and we're going to measure the force there. And so I'm doing the same thing, pulling it at constant velocity. That's less than 2 newtons. It's actually close to 1 newton. So that's a big difference in the frictional force, big difference in the coefficients of friction between the aluminium surface and the rubber surface. Now, this is just the wood surface, I think. But it's nice sanded smooth wood. Let's see what I get here. So that's about 3 newtons. That's in between the polished aluminium and the rubber. And that makes sense to me, right? I know, I can feel the aluminium was smooth. I know the rubber, it had a lot of frictional force. It adhered to the tabletop a lot. So that the wood was in between makes sense. And then there's this last sort of plastic surface. And we're going to do that one. And that has the lowest friction of all. You wouldn't want to walk on a plastic sheet. I've actually done this when I've been, I don't really decorate the house, but I have decorated the house, painted the house, and you put down plastic sheet. Every time I fall over on the plastic sheet because there's not much friction to hold you in place. Okay. Too much detail there, I think. Let's stop sharing that one. And let's see what I'm going to do next. Actually, I've got a feeling I'm going to show another. Oh, no, I'm going to show you a table. So here's actually a table of coefficients of static and kinetic friction. There's a mu s and a mu k. And let me just point out, I don't want to linger on the numbers, but oops, so I'll do that, I guess. Rubber on concrete, right? It's a car on a road. Look at these static friction and kinetic friction numbers. They're close to 1. That means a lot of friction in that case. Look at the human joints. I don't know anything about medicine, but I know I've got joints, and I know there's some fluid in there that between the cartilage, and there's almost no friction there in your joints. And you want that, right? You don't want to be having lots of friction in your joints. And so those are 2 classic examples of high friction coefficients and low friction coefficients. I want to show a little video clip here. So I'm going to share another screen again. And, from the way I've been talking, like friction is kind of a nuisance. It's like, I wish we lived in a world without friction. It's just annoying. But that's actually not true. We would not be able to walk. We would not be able to run. We wouldn't be able to bike, or we wouldn't be able to drive with friction. And I'm just going to show you a little movie to make that clear. So when you have snow, ice on a road, you know that ice and snow make the roads slippery. And it's only because of friction we can drive safely. And so here's just a little reminder of that.
Uh-oh.
So friction is important for us. We would not be able to walk without friction. We wouldn't be able to bike without friction. We wouldn't be able to drive without friction. And so it sometimes feels like a nuisance, but it's not it's a necessity. Let me go back to the slides. And so now let me, in the last 25 minutes, look at an example or two of Newton's laws, but now involving friction. And so let's first revisit this problem. We can do this one pretty quickly because we did a version of this problem in the last class. But in the last class, we said that the incline was frictionless. In this class, we're going to have friction on the incline. So I've got this 12-kilogram cart, shopping cart, and it's sliding down this 5-degree incline. This is a 5-degree incline here. And what we're going to figure out is the acceleration of the cart down the incline. And the difference between this version of the problem and the prior class version of the problem is that now there is friction on the incline. There's kinetic friction on the incline, and we're going to incorporate in our calculation of the acceleration the effects of kinetic friction. And we're told the key numbers we need in this problem. Let me get the annotation back. The key numbers are, well, we got the mass of the cart here. That might be useful. We got the angle of the incline here. That's going to be useful. And we got the coefficient of static friction here, 0.03. And as I say, it's just the number, dimensionless, unitless. So let's solve this problem for the acceleration. I think I'm going to skip that. We've had too many demonstrations. It's so costly for me to change screens that the class would run out before I go back. Okay, so you know, I even annoy myself by saying this for every problem, but I'm going to annoy myself and say it again because you want to draw a diagram. Really want to draw a diagram on these problems. They help you picture, visualize, understand the forces they're acting. So this slide is my force diagram and statement of non-equilibrium for the shopping cart on the incline. So in brown here, I've got, let me get my pen going again. Here's the incline. Here's the angle 5 degrees. Here's the block in blue. Here's the mass, 12 kilograms. And then I've added, this time, 3 forces, 3 separate forces. Gravity downwards, that's the W here. There's normal force. It's perpendicular to the incline, that's the rule for it. And then there's frictional force. And that's parallel to the incline, parallel to the surfaces. That's the rule for it. So now we got these three forces in red, blue, and green. And it's those forces that are going to add together to make the net force and determine the acceleration down the incline. And look, the object will slide down the incline. That's why friction opposing that motion is acting up the incline. Now, I did add one more thing because we're going to want to use this. When we solve these problems on the incline, if you remember from last class, we resolve the incline, we resolve the forces on the incline into directions that are parallel and perpendicular to the incline, what I labeled X and Y here. And whilst the friction force and the normal force are already either parallel or perpendicular to the incline, weight is not. And so I'm resolving what we call resolving weight into a parallel component, W sine theta, and a perpendicular component, W cosine theta, exactly as we did in the last class. But anyway, here's the expression of non-equilibrium in this case. The fact that if this car is accelerating down the incline, then the sum of these three forces, weight, normal force, friction force, they add up and they make a non-zero force, a net force, a total force that's not zero. And that's gonna cause the acceleration. And that's how we're gonna find the acceleration. Okay, so let's go from the picture to the calculation. And that's what I'm doing here. So all this stuff upstairs here, I just talked about on the last slide. I'm just reproducing the picture and this overall idea of equilibrium here. But what I'm going to do is, and what we generally do on an incline like this, or in many problems involving equilibrium, non-equilibrium, is we resolve forces into, say, horizontal and vertical components, or in this case, into components parallel, perpendicular to the incline. And so that's what I'm doing downstairs here. That's the new stuff, right? Fy, those are the forces acting perpendicular to the incline in this y direction. Fx, those are the forces acting along the incline, parallel to the incline in this direction here. And so I'm going to write down the equilibrium condition, but as two equations now, equilibrium in the y direction, equilibrium in the x direction. The interesting thing about that is that in the y direction, right, you know, that block doesn't jump in the air, it doesn't crash through the incline. That means that there's a balance of the forces in the y direction. On the other hand, in the x direction, that block does accelerate down the incline, downwards, so that there is no balance in the x direction. So what we're really doing here is separating out a portion of equilibrium from a portion of non-equilibrium, so that we get a better perspective view of the problem. Okay, so let's apply this would be Newton's first law, that if the forces add up to zero, there's no acceleration. Let's apply that for this y direction. In the y direction, there's a portion of gravity downwards. It's this guy here. And then there's the normal force upwards. That's this guy here. And they must add up to zero. And if you think about it, that tells you what the normal force is. The normal force must be equal to the weight times cosine theta. So that's going to be useful to us, actually. If we go to the second equation, right, that's for the motion along the incline. Well, there's a portion of gravity acting along the incline. It's this guy here. It's downwards, so there's a plus sign. And then there's a friction that's trying to oppose that. And this is the friction force. But I've written it as, remember, that coefficient of kinetic friction times the normal force. So the formula for the frictional force are plugged in there. And the minus sign is that this force is opposing the motion. It's in the negative x direction. The weight, component of weight, was in the positive x direction. And these two guys add up, and they don't make zero because they are what conspire together to make the acceleration. And so this is the second law applied to the horizontal direction. Well, if you look at this second equation here, and you realize that you know that N, the normal force, is W cosine theta, just using this, you can use this equation to actually calculate this acceleration. And so that's what we're going to do. Having plugged in, replace the normal force with the weight times cosine theta, we'll solve this little equation here for the acceleration and come up with our answer. And that's on the next slide. So let's do that. And so here we are on the next slide. And this is the last slide on this problem. This is solving for the acceleration. So now this is much more just mathematics, really. Here is the equation from the last slide. Except I put in the normal force as W cosine theta. So that was the equation from the last slide. And you can see that if I just divide through by the mass, that gives me an equation for the acceleration. So the acceleration is this difference between the weight times sine theta and the coefficient of friction times the weight times cosine theta divided by the mass. And actually this is even simpler than this looks, because the weight itself, right, this is mg. This weight is mg. And so the mass in the denominator here will cancel with these masses in the numerator. And the equation that you get is simply this one here. That's the acceleration down the incline. In terms of, what's it in terms of? It's interesting. It's in terms of the acceleration of gravity. Of course, it wouldn't accelerate down the incline without gravity. And then it's in terms of the angle of the incline and the coefficient of friction. And if you look at this little equation, it's really an, I want to say the word enjoyable equation. I don't know if that appeals to the audience, but think about what it's telling you, all the interesting stuff it's telling you. It tells you with this G, right, if you went to the moon, the acceleration would be less. If you went to Jupiter, it'd be more. It tells you with the theta, right, how things change as you order the angle of the incline. If you make the incline steeper, you're going to increase this acceleration. Make it less steep, you decrease this acceleration. And finally, there's this new piece we've not met before. It tells you how friction influences the acceleration. It's going to reduce it because it's minus sign. And if there's lots of friction, it'll reduce it a lot. If there's a little friction, it'll reduce it a little. If there were no friction, it was frictionless, this piece goes away and you just get G sine theta. So it's a really nice little equation, I think, that pops out and carries a lot of understanding about how friction works, how the incline works in slowing down the pull of gravity on the block. Of course, we can solve it numerically, right? We know the acceleration of gravity, we know the angle of the incline, we know the coefficient of friction. You plug in all the numbers, and here's the answer to the question. The acceleration down the incline of the shopping cart was 0.56 meters per second squared. Okay, so that's a fun problem. And I think we got time for another one here. And here's the next one, which is also a non-equilibrium friction problem. So in this particular problem, we're told that we've got two crates containing fruit, peaches over here on the left and apples over here on the right. And there's 10 kilogram crate on the left and 20 kilogram crate on the right. Now, the two crates themselves are connected by a rope. And then I'm pulling, say, on a rope on the right-hand crate with a 50 Newton force. We're told that these crates are going to slide across the floor. Here's the floor. And so there'll be friction between the floor and the crates, and we're told the coefficient of friction. And the question asks us to figure out the acceleration of the crates and the tension in this cable or this rope. So those are the two things we're going to figure out. So just to summarize, right, we know the mass of the left-hand crate, 10 kilograms, mass of the right-hand crate, 20 kilograms. We know the force I'm applying, and we know the frictional force. And we're going to solve for acceleration, and we're going to solve for tension. I got a little movie of this one, so let's just watch it quickly, if I can. And so here you see the crate of apples. I'm putting it on the bench top. And then here you see the crate of peaches. I'm going to put that on the bench top. And then I'm going to put together this arrangement of the two crates connected by, the crates connected by a rope between the crates. And then I'm going to pull on a second rope, apply my 50 Newton force on the second rope, and pull the arrangement over here towards the right-hand side. So what's going to happen now is exactly the situation in this problem. And there's something about that I felt, it was very relaxing to do it. It was very therapeutic to do that. And it was so relaxing and therapeutic. And I thought it'd be a nice movie moment to pull it back the other way. And we can all just calm down and not worry about the test for a moment. Okay, but now we can get back to worrying about the test, and let me share the slides. And let's go ahead and solve this problem for the acceleration of the pair of crates. So the first thing I, of course, did was to draw the forces that are acting. And specifically here, I've drawn the forces that are acting on that crate of peaches and on the crate of apples. So over here on the, I got to get my annotation back. If anybody knows how to keep the annotation on, put it in chat, because it's starting to aggravate me, frustrate me. Okay, so here's the peaches, and I've drawn 4 forces here in these different colors. These are the 4 forces that are acting on the crate of peaches, and they're all familiar to us. They're in fact the cast of characters in today's class. Weight downwards, normal force upwards, tension towards the right, and friction opposing the motion towards the left. And those are the forces. I labeled them with 1s because I'm going to, this is crate number 1, and it has mass M1. And so it's weight 1, normal force 1, friction force 1. Here's the same thing for the 20 kilogram crate of apples. That's crate number 2. Again, there's the full list of characters here. There's the weight downwards, there's the normal force upwards, there's the tension force due to the rope between the crates, there's the friction force opposing the motion. But there's also in this case my force that I'm exerting towards the right to pull the whole arrangement. And so those are the forces that are involved. I did note when I wrote down these forces, right, the friction force in both cases is related to the normal forces. So I wrote that down here. And in turn, right, the normal forces are equal and opposite the weights. So in fact, the friction forces, because they're related to the normal force, which is related to the weight, they are related to the weight in both cases, and the mass in both cases. Okay, so that's the diagram that I made, quite proud of it. And let's go to the next slide. Next slide, I said, well, look, all the real action in this particular drama is happening in the horizontal direction. And so I'm really going to focus on the forces that are in the horizontal direction to solve this problem. So let me just make things seem a little less complicated by forgetting about the weight, forgetting about the normal force. The horizontal forces that are acting are the ones that are going to cause the horizontal acceleration. And so it's the horizontal forces that I need to worry about to figure out the horizontal acceleration. And so for the box on the left, right, the only horizontal forces are friction and tension. And I made it clear on this slide that I actually know the frictional force. Not only its direction towards the left, but its strength, because it's the coefficient of friction times the normal force. And the normal force is equal to the weight, or mg. And so the frictional force on the left-hand blocks is coefficient of friction times its mass times the acceleration of gravity. And that comes out to be 9.8 newtons. We know each of these numbers, 0.1, 10 kilograms, 9.8 meters per second squared. So that's nice. We know this frictional force. It's not like some mystery. And the same thing applies to the frictional force on the second crate, right? It's related to its normal force, which is related to its weight, which is related to its mass. And so this frictional force is the coefficient of friction times the mass of this crate times the acceleration of gravity. It's a 20 kilogram, not a 10 kilogram crate. And so you get 19.6 newtons for that frictional force. And so looking just at the horizontal forces and knowing the fact that we actually know both my external pull of 50 newtons and the frictional forces, there's less unknowns in this problem than might have seemed in the first place. Only the tension force, which is something we want to figure out here, is unknown. Okay, next slide, if I can. Okay, so in this slide, I'm going to solve the acceleration. It's not a hard calculation at all to solve the acceleration, but you've got to think about things the right way. And that's the key point about this. So to solve for the acceleration, I'm going to actually sort of step back a little bit. Stepping forward a little bit. I'm going to step back a little bit and not think about the individual crates, but think about this whole system involving the two crates and the rope. That system has an acceleration, just like the individual crates also have that acceleration, and the rope has that acceleration. That system has the acceleration. I'm going to figure the acceleration of that system. And that system, if I want to think about that system, it's a system that has it has a mass of 30 kilograms because it's made out of the two crates. And the external horizontal forces that are acting on that system are simply friction forces, these two downstairs here, and my force, this one upstairs here. And so we actually, if we think about that system, we know what we would call the external forces that are acting on that system. We know them. We know their sizes, we know their directions, and so it's not hard to figure out the acceleration of that system. And when you're figuring out the acceleration of that system, you don't have to worry about what we call the internal forces. So those tension forces in the picture, these guys, they are within the system. They're between parts of the system. They can't get the crates moving. They couldn't slow the crates down. They couldn't speed the crates up. They're just within inside the crates system. It's only the external forces, the friction force and the force I exert, that can accelerate the system. And so we can just ignore the tensions that are inside the system, that are internal forces, when we try and calculate the acceleration. And so with those arguments, so this is the challenging bit to me in solving this problem, not the math or the equations, but to reason out how we're going to solve it by thinking of a system, by ignoring the internal forces, the tensions, and by just focusing on the external forces, my pull and the frictional forces. Then we can find the acceleration. We can find the acceleration by Newton's second law, that the acceleration is the sum of the forces divided by the mass of the system. The three forces are the friction on the first crate, friction on the second crate, my pull on the crate on the right, and then we just got to divide that by the mass. All those forces we know. Minus 9.8 newtons to the left, that's minus 19.6 friction newtons to the right, that's my pull of 50 newtons. The friction force here should be to the left. And then there's my pull of 50 newtons to the right. And I just divide that sum of forces by the 30 kilograms, and here's my acceleration. And so out of that comes a solution for the acceleration. Once you've got that, it's actually, oh, I didn't mean to do that at all. That was a stupid mistake. Share screen again. Once you've got the acceleration, the second part of the problem of finding the tension becomes very easy. So let me just show you that, but it is much easier now. Our life has suddenly become easier. So to solve the tension now, all you need to do is actually think about either the left-hand or the right-hand crate. And I thought about the left-hand crate, but you could think about the right-hand crate. And apply Newton's law, second law, to the left-hand or the right-hand crate. And so what I'm doing here is applying Newton's law's second law to the left-hand crate. But equally well, we could have thought about this crate on the right. Anyway, the law says that the sum of the forces equals mass times acceleration. So the sum of the forces for this left-hand crate are, here's the friction force acting on it. We know that. Here's the tension force acting on it. We don't know that. Those forces add up to make the acceleration, and we know the acceleration and the mass. So you can turn this equation around now and solve it for the tension. The tension, if you rearrange this equation, just take the frictional force from the left-hand side to the right-hand side. The tension will be mass times acceleration plus the frictional force. Here's the mass times the acceleration, here's the frictional force, and here's the tension force. Here's the tension force in the string. As I say, you could have found the same thing by thinking about the other crate. You would have still got 16.7 newtons. Okay, let me end there. We've looked at today the frictional force, and we looked at more examples of Newton's laws in the presence of gravity, normal, friction, and there's one more, tension forces.